Okay, I think we can start. Good afternoon, or morning, or evening, everywhere. Welcome to this fourth session of this spring school. So a couple of announcements before we begin. There will be one tutorial session after the lectures today. So that's from 5 to 7 UK time, and there will be a morning tutorial session. So tomorrow from 10 to 12. So there's a double tutorial session between today and tomorrow, so that you are aware of it. Although it's in the timetable, all the information you can see it on Mural about. Lecture notes, exercises, announcements, and so on. You can disconnect the subtitles in your Zoom session if you want to. Sometimes they get if they are on, they can be a bit annoying or entertaining, depending on your taste. But you can always switch them off. Also, if you want to ask any questions, you can raise your hand, but then the usual announcement that you probably know that you will be recorded. So if you prefer not to, you can always use the Q&A box. I'll keep an eye on that, or the chat, but preferably the Q&A, and I'll pass these questions on to the speakers at the end of each talk. I think that's more or less all the announcements. So today we have 3 lectures, which are a continuation of what we started yesterday. So we'll have from 2 to 5 Philippe, Trinh, and then 3 to 4 Kemal, and 4 to 5 Daniel, continuing on the material that they started yesterday. So without any other thing for me to say, I'd like to pass to the first speaker of the session. So please.
Thank you very much. Just before we start, a quick note to the students. I've been really impressed by how everyone's worked during the tutorial, so do keep up the good work. My initial design for this talk, I've decided to scale it back a little bit, because what I noticed during the tutorials is that some students really struggle a bit with calculations. And so in this lecture, I'm going to go in detail into some of the calculations. So I know there are a lot of senior people in the audience, but this is mainly for the students to learn about some of these techniques. Okay, so this is the second of 3 lectures on exponential asymptotics for physical applications. The first one was yesterday by Chapman, and I'm doing the second one on fluid mechanics and applications to waterways. And then John King will run the anchor leg on multiple scales. And we're going to start off with just doing a big review of what John taught you yesterday on applications to nonlinear differential equations. The basic idea is that you have a nonlinear ODE, or maybe even a PDE, but I've written an ODE here in terms of y and its derivatives. And you do the usual thing, which is to expand it into a perturbative expansion in powers of this small parameter epsilon. In doing so, you notice that there are singularities in the earlier terms, and these singularities have the effect that they will magnify, and that produces usually factorial overpower divergence, but not always. But in most cases, the divergent form that you can expect is a factorial overpower. Why do you do this? Why do you try to find this late orders divergence? Well, that's all explained by the next few steps. The series diverges, so you try to truncate the series after n terms, and now our goal is to try to find this remainder, which you expect, you're hoping to find is exponentially small if you truncate optimally. That yields a equation for the remainder. You can linearize the equation for the remainder, and crucially, it's forced on this right-hand side by a term that involves an order epsilon to the n error, because you've truncated after all, and so you have this order epsilon error. So this is really the key part of this slide, which is to recognize the fact that as epsilon tends to 0, the optimal truncation point n tends to infinity, and therefore this gives you a crucial relationship between the remainder that you're trying to find and the late order terms. And that's sometimes why when people do this exponential asymptotics business, they say you're decoding the divergence. You're using the divergence to tell you something about the remainder term. The remainder term will involve those exact components of the divergence that you predicted earlier. So the A here and the chi here, the singulant chi, which appears now in the exponential. And as Chapman explained, your goal is to now find a differential equation for this Stokes multiplier, this S of Z. And in doing so, you'll find this boundary layer phenomena across the Stokes lines. There's a criterion, almost a universal criteria that you can apply to find the locations of those Stokes lines, which is, in this case, the imaginary part of chi is 0 and the real part of chi is greater than or equal to 0. So equal phase and maximal dominance, okay? And this, just to keep in mind, this is a problem where the base series, this y, it has an exponential e to the 0. Otherwise, this Stokes line condition would involve measuring the relative singulance between two exponentials, okay? But for the problem that I'll present here, this is the Stokes line condition. So this is the methodology that, that was laid out in lecture 1. Okay, so now I'm gonna tell you some interesting history about water waves, okay? And I think it's suffice to say, the study of wave structure interactions, this is a classic, historically important subject that continues to have great scientific and industrial importance. But crucially for us, right, the key is that there's some exponential asymptotics here to be done, and it links to observable phenomena. So that's the nice thing about studying applications of exponential asymptotics to water waves. Not only are they kind of fundamentally scientifically important questions, but they relate to observable and computational phenomena. This is a picture from J. Scott Russell's famous 1845 report on waves, just to show off, the variety of behavior that you can have in wave structure interactions. Everything from overturning waves to vorticity to white cap forming on the surface and ripples of all sorts of different kinds. So the kind of the main traveling wave waves here, and then the small scale ripples here. So this is something that you hope to explain. Okay, so now what does this relate to what does it have to do with exponential asymptotics? Well, in the public lecture, John Chapman kind of noted this low Froude paradox that was first highlighted by a naval architect, Francis Ogilvie, in '68. So I'm going to tell you about this low Froude paradox. The situation that you want to keep in your mind is that you've got two-dimensional flow over this rigid, this obstacle here that has some length scale L. You're looking at steady state flow. U is the incoming speed of the stream. And if you fiddle around with the dimensional quantities, you will come out with a governing non-dimensional parameter, which is the crucial parameter, this Froude number here. So this parameter here measures the relative strengths of inertial and gravitational effects. This is the epsilon. So we're going to be looking at the limit, the epsilon tends to 0, low Froude, or you can think of it as low speed flows. And this is 1968, unpublished. I mean, it's a technical report from the University of Michigan by Francis Ogilvie, and he notes, in attempting to solve a problem involving the motion of a body near a fluid-air interface, one generally linearizes the boundary conditions at the free surface. This is a matter of sheer necessity, for otherwise there's little hope of solving anything. He goes on, generally, if the first linear approximation is a poor one because the perturbations are too large, there cannot be very much hope of improving it with higher order terms. A remarkable exception to this rule appears to have been found by Salveson in '68. This is another unpublished report. We have shown that under certain conditions, the second order solution dominates the linear solution. It appears paradoxical that it should be necessary to include higher order approximations at very low speeds, for the total disturbance becomes smaller and smaller as speed is reduced more and more towards 0. One should expect the assumptions required for linearizing ought to become steadily more nearly valid as the free surface deflection decreases. Instead, the problem appears to become more nonlinear. So it's a little bit cryptic what he's referring to, and it's not quite clear what he's referring to. He's referring to the singular nature of the epsilon to 0 approximation and how something funny seems to be at work when you try to develop wave approximations to that problem. And I won't say more about that, except that over the next few decades following Ogilvie's '68 paper, a number of people tried to go into this area of developing low Froude approximations, and similar cryptic statements appear in the literature. Here we have someone, Tulin, who wrote in 2005, very recent in comparison, does an asymptotic low speed theory of thick ships really exist? And if so, what is its correct form? And then another 1983 paper by Tulin. The most important comment to make is that for a given epsilon, no matter how small, this so-called low speed theory is not valid for sufficiently low speed. It is a theory valid for low, but not too low speeds. Really confusing what that means. How can something be valid for low but not too low speeds? Okay, so this is just my example of a little expose of the confusion that existed within this area. And I don't want to diminish all the contributions from people from the 70s and 80s. A lot of people developed theories to try to explain these low speed waves or low fluid waves, but none of them had that some of the necessary equipment of exponential asymptotics, the explanations from Stokes lines and the Stokes phenomenon that we know now today. So this is what I want to present to you. And this talk is going to follow some of the work by Chapman and Van den Broek from 2006. Okay, so the situation that we're going to look at is flow past, it's a model problem, two-dimensional potential flow past the body of a ship. So this is the figure on the left here is the rear side of the ship, the stern of the ship that you've modeled as a semi-infinite body. Okay, and you're interested in trying to find this potential, which relates to the velocity of the flow. Okay, now in this talk, I'm mainly going to be working with, just for simplicity, sigma equal to 1/2. So that corresponds to a rectangular stern here. So sigma relates to the angle of the single corner. Okay, so the task is for you to solve Laplace's equation within the fluid. You have no penetration conditions on the solid and fluid boundaries, so this kinematic condition. And then you also have a dynamic condition. This is known as Bernoulli's equation on the free surface. You notice the epsilon appears in here. So there are three reasons why this is a tough problem to solve. It's a very hard problem to solve. The first reason is that the geometry is quite complicated, right? The second reason is that the free surface is unknown. You don't even know where the free surface is, so it must be solved as part of the problem. And the third reason is that the Bernoulli's equation is nonlinear, and that causes a lot of difficulties in developing analytical methods. So you have to take some kind of approximation. You have to look at the limit, for instance, of epsilon tending to 0. Okay, so there's a second trick to solving these problems, these potential flow problems, and the trick is to invert the formulation. I've already introduced to you the potential function phi, and this potential function has a harmonic conjugate called the stream function psi. The stream function is it's constant along surfaces. So I can set the stream function to be 0 from A to B to C to D. So this is what you see on the picture on the right here. A, B, C, D. In the phi psi plane, the boundary A, B, C, D has been mapped to the real axis. Okay, and so you think of things in terms of this W, so-called complex potential, and crucially, rather than thinking of W as a function of Z, this is what we usually try to think of, phi as a function of X and Y, you invert that and you think of Z as a function of phi and psi. And the advantage is that if you invert this formulation here, then you solve in a domain which is very simple. It's just the lower half plane. Okay, so that's the first step to kind of reformulating this problem in a tractable way. The second step is that you may not want to be working with Z, X and Y, just trying to solve for X and Y. Rather, you'd like to solve for the velocity components. It just makes the formulation a little bit easier. So for this talk, I'm going to be working with a streamlined speed Q in an angle theta. So that is to say, if you take a particle of fluid in your system and you follow it along the streamline, it'll have some angle, we call that theta, and it'll have some speed, we call that Q. So these will be the two unknowns in our problem as a function of the complex potential W. Okay, right, so the governing equations are as follows. You firstly have Bernoulli's equation posed in terms of your Q and theta variables. So this is the nonlinear equation that was causing us a lot of grief. And secondly, there's a way to repose in essence, Laplace's equation. So rather than solve Laplace's equation within the bulk of the fluid, which is a two-dimensional problem, it's difficult, right? The trick is that you apply Cauchy's theorem and you integrate around the boundaries. So in this case, A to B, if I go back to my previous picture, you integrate from A to B to C to D, and then a little semicircle that you send off to infinity. And that reduces the problem to essentially determining that Q and theta should satisfy a boundary integral equation. So you have Bernoulli's equation and a boundary integral equation, which is integrated on your solid surface, which runs from minus infinity to 0, and then your free surface, which runs from 0 to infinity. This little dash here is the Cauchy principal value. This dash in the integrand, if you've not encountered it before, all it is that this integral is singular when this variable of integration phi here is equal to the original phi. So you subtract out the little indentations and you integrate to epsilon left of this phi and then from epsilon all the way to infinity. Okay, so that's the Cauchy principal value. Now you know for this integral, you know the values from minus infinity to 0. If I go back to this picture here, I know that the angle of the ship is 0 from A to B, and then it's either pi sigma, or in the particular case that we're looking at, pi over 2 from that point on. You put that into the integral, and now you've reduced it down to an integral equation that needs to be determined from 0 to infinity. So just to be very clear, just so everyone's on board, you're looking for unknowns Q and theta as a function of phi. These are equations along the free surface when psi is equal to 0. Phi ranges from 0 to infinity, and you assume that there's a stagnation point at the connection between the solid boundary and the free surface, and you assume that the waves are traveling towards the right. The second condition is not so obviously necessary. And that's it. I should say, by the way, that the stagnation point assumption is not obvious. It's not obvious that you should be imposing a stagnation point, but I'll leave it at that. Okay, so I want to we can do the most basic thing and just look at what happens when epsilon is a small number. If epsilon is a small number, you see sine of theta is equal to 0, so therefore theta is equal to 0. So this tells you that when the speed is very small, that has the effect of basically flattening out the free surface at leading order, or the other way of thinking about it is that gravity is infinitely strong and it presses down on everything. This is what's known as the rigid body solution or rigid lid solution, or the double body solution. I'll tell you why double body in a second. You can then derive the leading equation for Q naught, and it gives you this. So if I plot that profile, this is what I have on the right. Notice that Q is 0 at the connection between the solid boundary and the free boundary, and then it tends to 1, tends to uniform flow downstream. So that looks all very good. If you are wanting to go back to physical space from Q and theta, you can integrate certain relationships for that, and you can recover the streamlines of the flow. So ignore everything in the upper half plane for now. The lower half plane is that leading order solution we had before, where the free surface, which runs from where the mouse cursor is here in the center to the right, that's now been flattened out, and the body is on the left at that point. You'll notice that if I integrate these relationships and I try to solve for the streamlines, I'll also predict that there's a mirror image on the right. And that's why it's sometimes called the double body flow, because for this leading order approximation, it's equivalent to flattening out the free surface and then putting mirror points about that axis corresponding to the structure. Okay, let's now talk about numerical solutions. I want to give you another perspective of how to solve these problems, and just for us to be a little bit more familiar with working with this formulation. Okay, there's a very simple numerical algorithm to solve this problem, and I'll explain it as follows. So the first thing is that you're going to come up with an initial guess for theta. So for instance, I could just set theta to 0 because I know when epsilon is small, theta is near 0. The next step is I'm going to distribute a series of mesh points that run from 0 to a large number. So here phi 1 through phi n. And in addition to that, I'm going to distribute a series of midpoints between those indicated with the red squares. Okay? So the reason why I do this kind of main point, midpoint is that it's a bit of a cheat that allows me to integrate this singular principal value. If I integrate over the main points, for instance, phi 1 through phi n, and I evaluate at the midpoints, I can avoid those singularities. It's not a very accurate scheme, but it works for our purposes. You can come up with more accurate schemes for resolving this principal value integral. Okay, so the boundary integral gives us n-1 values for qi to the midpoints of q using the values of theta. Bernoulli's equation gives us n-1 equations. And we have a system of n unknowns. and you can close the system with the condition at the origin. Okay, so now I'm going to flip, now if this is going to work, I'm going to flip to MATLAB, and I'm just going to show you what it's like to just solve this. You can even do it in 23 lines of code that I've done. It's really compressed code, but you can see this, I mean, you can read it over on your own time, but I set out the mesh points and I solve Newton's method for the differential equation. Okay, I can run this. Let's have a look. This is pretty fast. It's only 500 mesh points, and the value of epsilon here is 1. And we look at the picture. Here's the picture that results. So the full numerical solution is given in solid, and the dashed line is our leading order asymptotic solution. So very clearly, the leading asymptotic solution doesn't capture any of those free surface waves. The waves are quite large in this case, and so that's the question. How do you find those waves? You can argue just similar to the arguments that John Chapman had presented yesterday, that you would not expect wave contributions at any subsequent order. If they didn't appear in the very first order, because of the way the singular differential equation occurs, you're not going to expect an oscillatory component in the subsequent orders. So already you have the slight intuition that these are exponentially small, these waves are exponentially small, and if I was an experimentalist, I would go and try to measure these amplitudes and I plot them as a function of 1 over epsilon. I do some semi-log plots and I try to extract out that exponential dependence in preparation for the asymptotics to come. Okay, all right, so let's go on. Right, so now I'm going to show you how to do the analysis, and it's going to use exactly those techniques that we learned yesterday, that John Chapman taught yesterday, okay? Before we do that, we have to allow our governing equation to work in the complex plane. So currently, our governing equations, which are written here in white and in yellow, one white for the Bernoulli equation, yellow for the boundary integral equation. This is for phi being a real valued independent variable, right? But we want to allow phi now to be complex value. We do this in anticipation of the fact that we know there are probably going to be singularities in the complex plane. Okay, so we can set phi to be phi r plus I phi c if you like, and now we're going to consider phi to be complex. We're also going to do a slightly confusing thing and send phi to w. So I'm going to relabel the complex version of phi with the previous complex potential. Okay, either this confuses you or it doesn't, but it's important for you to remember that you're operating not with physical flow field variables. The W is not the one that corresponds to the physical phi and the stream function phi. It corresponds to an analytic continuation of the free surface quantities. And then now Q and theta will be complex value. So you take Bernoulli's equation, and Bernoulli's equation is very easy to analytically continue. You just change the phi to a W, and you just treat this as an initial value problem, if you like, allowing you to walk all over the complex plane. The boundary integral equation is a little bit more difficult to work with, but essentially, you're interested in taking this phi here on the left and then popping it off either into the upper half plane or in the lower half plane. And in doing so, you produce the version to the right here. Notice the integral on the right here is no longer has a dash through it. It's no longer principal value because W here lies in the upper half plane. In this case, I've moved it into the upper half plane, and I'm integrating along the axis. And if you don't believe that this is the analytic continuation, you can just send W back onto the free surface, and you'll pick up a residue contribution, which will cancel with this I theta and return you to the original dashed integral. Okay, so at the end of the day, this is the formulation that we're going to be spending the next couple minutes working with. We have Bernoulli's equation for Q and theta, and we have a boundary integral equation here. Now, in what follows, I'm going to write this boundary integral with this Hilbert notation. So I've called it H hat. So H hat is my, you can call this boundary integral the Hilbert transform. This is the Hilbert transform of theta, where W is the independent variable. I use a hat here just to remind myself that it's complex, that W is complex. Okay, right. So what were the steps that we taught you yesterday? The steps as follows. You start off setting Q and theta to be its regular perturbative expansion. You find the early orders. then you try to write down the order epsilon the n terms. And this is a thing that I want to kind of help the students a little bit with, because everyone's a little bit confused. Which terms do I keep at order epsilon the n? This is a nonlinear problem. It's difficult to see what you should be keeping and what you shouldn't be keeping. Once you know which terms to keep, you try to put in your factorial over power ansatz, and then you try to determine some of those components that allow you to characterize the divergence of those late order terms. Okay, so we're going to try doing this on the blackboard, and it's either going to go very wrong or it's not. Okay, so in order to speed things along, I've written out all the necessities at the very top here, and hopefully you can see what it corresponds to. I'm going to use white for Bernoulli's equation. I'm going to use yellow for the boundary integral equation. We're going to substitute our two expansions of Q and theta in, and the very first few orders are easy. I have a little cheat here of the expansion of the nonlinear terms of the sine theta and the log Q, and this is just something that you can work out in your own time. So if you remember yesterday, well, when Chapman did his talk, he talked about an f of phi on the right-hand side, and that was Taylor expanded. It's the same thing. Our f of phi here is either sine theta or log of Q. Okay, but we need this little cheat just to help us along a little bit. The order 1 expression is very easy to see. As we said, you can set epsilon equal to 0. You have sine of theta equal to 0, so theta is 0. And I have Q naught is equal to W over W plus 1. So already you see that there are two singularities, one at the stagnation point at W is equal to 0, and one at the what previously corresponded to the corner of the stern at -1. Okay, then you can go to order epsilon, and there it is. Okay, now the thing that you want to pay attention to is this first equation here, Bernoulli's equation. You notice that theta 1, the next order that I need, depends on the derivative of Q naught. And this is basically the trend for any singular perturbative problem, that whenever you find a subsequent term, you're differentiating the previous terms. So any singularity that appears in the previous terms will then be magnified. You end up adding to the power of that singularity as you go further and further down the hierarchy. Okay, right. So now we want to do the order epsilon to the n terms. And that's where it begins to get a little bit hard. And I'm going to do yellow here. I'm going to do the boundary integral first, because there's a very important simplification that it provides. Okay, so I go to the log Q here and I look at my little cheat sheet, which tells me which terms I need. So I'll write that down. So at order epsilon to the n, I need a Qn over Q naught minus Q1 over Q naught squared, Qn minus 1, and if I like, I can also write plus order here, Qn minus 2, just so you know what I'm dropping in that expansion. Okay, I'm going to then have an I theta, so that plus I theta n like that, and on the right hand side, I just have the Hilbert transform. This is part of the order 1 expression. The Hilbert transform, this h hat of theta n, like so. Okay, so now there's a very important simplification that you do when you do these kind of boundary integral problems for potential flow, which is that this guy is actually exponentially subdominant. And there's not an easy way to explain at this point why you get to assume that. So I'm just you have to take it on faith. So I'm going to claim that this is exponentially subdominant. Well, I can give a hint of the reason why this is the case. As n tends to infinity, you're interested in the limit, the late order terms n tends to infinity. I give a hint of why that's the case. Well, the hint is that basically the Hilbert transform, this h hat, is integrated along the axis, along the free surface. But the singularities lie away from the free surface. And it's because of that fact that the integration domain is further away from the singularities means that this guy is exponentially subdominant, but it's quite difficult to see at this point. What you do is you try to solve the problem making this assumption, and then you go back and you see, was that assumption actually valid? Okay, so this basically just gives you an equation for theta n. So I have theta n is, I move everything, this guy over the right-hand side and divide by my I, and that is equivalent to just multiplying the left-hand side by an I, like that. Okay, so I've got one equation now for my theta n, and I can substitute this one into Bernoulli's equation and try to get this equation for Qn. Okay, and that's the harder bit to do. Right, so I'm going to go to white now, and for Bernoulli's equation, I have to do the expansion of the quadratic. So I have to put in my series into the quadratic and into the derivative expression. And the trick is basically, well, there's kind of two tricks of doing these derivations. The first trick is that you only usually need the first two orders. So you only need the leading order as n tends to infinity, and you need the correction term, just like you do when you do WKB analysis. And the second trick involves the indices and the derivatives, but I'll explain that in a minute. So you basically start off with the highest indices. So you have a 2 q naught qn when you expand that first one, times a q naught prime from the derivative term. And then I'm going to start decreasing this index n to n minus 1, and then increase this index here. So this is a plus 2q1 qn minus 1 q naught prime plus dot dot dot. And I'm also going to need those order epsilon, and I made a mistake here. The mistake is that should be an n minus 1 and that should be an n minus 2, because if I need order epsilon the n terms of this first term, I need the order epsilon to the n minus 1 terms from the quadratic q squared q prime. Okay, so I need, the next term I need is a q naught squared times a q n minus 1 prime. And I'm also going to need the next one, that q naught q1 times a q n minus 2 prime, and plus dot dot dot. So you'll notice that basically I started off with the high indices for q squared and the low indices for q prime. And then these are the first two terms. And then I went to the high indices for the prime, and I started with the low indices, and you just decrease them in that way. And you'll also notice that I only started writing two terms from each, because I only think there's going to be two terms that I need. Okay, so then this is equal to, and then you go to our little cheat sheet here, and then you write down the expansion for the sine. So here are the relevant terms that you're going to be needing for the sine term there. So the first one will be a minus cosine of theta naught, will just be a minus 1 because theta naught is 0. And then theta n, but I know what theta n is here. Okay, so I'm going to put that in over here, and that has the effect of negating everything here. So that's a minus I qn. I should have done this in yellow, but it's too late now. Plus I q1 over q naught squared, qn minus 1 plus dot dot dot. You also notice that the next order contribution I wrote down here is theta n minus 1, which we would typically need. It's a little bit maybe near the edge of the screen, but sine of theta naught is 0, so you don't actually have that contribution. Okay, so now basically you want to identify what you think will be the leading order contribution and the next order contribution. And the trick there is that you treat your indices and your derivatives kind of on equal footing. You know that when you have a gamma function expression, we're going to eventually put in our factorial over power ansatz, right? That's the method, into these expressions. And so if I have an index of n, then the factorial will be greater than if I have an index of n minus 1. On the other hand, I know that if I take a derivative of the factorial over power expression, I'm bringing a factor of n up to the top because of the denominator. And so that's why n minus 1 prime would then be treated as equal footing with qn. So you think of your an index shift of minus 1 as equivalent to a derivative here. So I think that this one here will be leading order, and I think that this one here will be leading order as well. This qn minus 1 prime. And then after that, I think this will be second order here, or the next or first order if you like. In the limit that n tends to infinity, I'm going to need this one as well. This is an n minus 2 plus 1 from the derivative, and so that should be of equal footing to nqn minus 1 here, and I'm going to need this one here, and I'm not going to need this one here. Okay, so we've identified what we think are going to be the crucial terms. Hopefully you can see, and I've not been standing in front of the screen all the time. You can see now which are the crucial terms. So the next trick that I'm going to tell you is basically we're going to rearrange these things, and then we're going to put it into a way which will make substitution of the factorial over power ansatz a little bit easier for us to deal with. Okay, so my trick, my philosophy is basically move everything to the left-hand side, and I'm going to divide out by the qn. I'm going to kind of combine different qn's and then divide out by what I think is the leading term, and then that just makes substitution of the factorial expression a little bit easier. So the first one I'm going to write down is that one there. So you have a q naught squared times a qn minus 1 prime, and I divide out by the qn. The next one will be this one here. I have a minus I over q naught, but I don't need to divide by anything because I've already divided by the qn, so that should be just a 1 here. The next one here will be a qn minus 1. So I have a 2q naught prime times qn minus 1, and I think there's another one over here, and that should be a plus, by the way, because it's been moved to the left, and I have a minus here, minus I q1 over q naught squared, like that, and I have a qn minus 1, and I divide out by a qn like that. Okay, and then the very last one that I need is this 2q naught q1 qn minus 2 prime over qn plus dot dot dot. And I'll put that into braces like I've been doing with all the other ones. Okay, and there we are. We're expecting that the dominant balance will be between this one, and that all the other terms will then be involved with the next order contribution. Okay, and so then the next step is for you to substitute the ansatz that you think is going to satisfy this factorial over power ansatz. And in this case, it's just a standard 1. So we're going to let now qn twiddles q of w, an unknown function of w, times your factorial of n plus gamma over chi of w to the n plus gamma. And just like we showed you in the previous lecture, you're going to take derivatives of these and try to simplify the expression. So for instance, you're going to have a qn prime here. You take a derivative, the derivative of the denominator comes up. So I have a minus chi prime times a q, and then I'll have an n plus gamma times a gamma function of n plus gamma here over a chi to the n plus gamma like this, plus 1, sorry, like that. And then the trick is that you'll notice that this thing here, by properties of gamma function, is gamma function of n plus gamma plus 1. So that was this derivative and index correspondence I referred to earlier, and I'll also have a derivative of the q prime term, plus q prime times gamma function of n plus gamma over chi to the n plus gamma, like that. Okay, and then you do that as many orders as you need. In this case, you actually don't need to go very far. You only need one derivative. But for a higher order problem, it gets more annoying. One of the exercise questions, I think, is a 4th order problem. So students in yesterday's tutorial were having to work out 4 derivatives of this, which was a little bit painful. Okay, now I'm going to show you a different trick of doing it. Just how do I do it with Mathematica? So if I now, let's see if this will work. The other way of doing it is that you just use Mathematica for things. And I can, in Mathematica, I can put in my my different expressions, my factorial over power expression for Q. I can put in the indices, and then I can try to compute the ratios. By the way, that trick I explained to you before, dividing out by the Q, this was just so you can actually do these simplifications a little bit more easily in Mathematica, because when you try to simplify ratios of factorial functions, it's a lot easier than trying to simplify the gamma function itself. Okay, so you define our 3 ratios that we showed on the board, and then you just do a series expansion in the limit that n tends to infinity. So the very first ratio, as we expected, is order 1, and then the other terms will be order 1 over n and order 1 over n. Okay, so you can even do it pretty easily with Mathematica once you've identified which terms are relevant. Okay, so let's try to find one of the relevant functions here. Let's try to find the chi. We're not going to find the q, and I won't have time to discuss the gamma. But this follows a very similar methodology to the one that was done yesterday. So you can go there for additional details. But I want to just give you the flavor of how this is all done. Okay, so we know that the leading order contribution will come from 1 and 1 here. And so when I substitute in my ansatz, this one here will produce a minus chi prime. So I'll have a q naught squared times a minus chi prime. And then this one here will just have the usual 1 in the back there. and that's equal to 0. So that's at order 1 over n. This is at order 1. This is your order 1 dominant balance as n tends to infinity. So now you can solve for this chi and then integrate it. So here's your chi is equal to the integral from a w star to a w of I over q naught cubed, and I'll be a little bit more, just some dummy variable here like that. Okay, so by assumption, this singulant function is the thing that generated the divergence. So this w star will be chosen to correspond to the one of the singularities of the leading order problem, the -1 or the 1. Okay, and the next thing you would do is then you go to order 1 over n and dot dot dot. And when you go to the order 1 over n, you use the various ratios we found. You're going to find a differential equation for big Q, and that will allow you to solve for it. Okay. And so that's basically the end of that Blackboard presentation. This is kind of what you'd emerge with. So there's our factorial over power ansatz, okay? And we just found the chi component here. This is the crucial singulant expression, and the Q can be solved for. It can always, you won't necessarily always be able to solve for the Q function. You have to leave it as a differential equation. In this case, you can actually solve for it, and it involves this prefactor lambda, big lambda. And so at the end of the day, we've determined the big Q, we've determined the chi. The two things we've not determined of this late orders behavior is the gamma here and the lambda expression. Now the gamma you can find basically by matching to the thing that generated the singularity. So there was a discussion about this in the question period of the last lecture, which is that one simple trick is you just set n is equal to 0 and then you match with the necessary singular behavior of Q naught. The lambda expression here, this one is much more devious. It's often very difficult to get this lambda. What you have to do is you have to rescale near the appropriate singularity and develop the inner equation, and to develop a series solution of the inner equation, and to solve that recurrence relation that it involves. Most of the time, for most of the applied mathematical problems that we're dealing with, we don't actually care too much about the value of that lambda as long as it's not 0, okay? And I'll say a little bit more about numerical checking of some of these relationships in a moment. Okay, so we determine our late order terms, and then now this is a big slide, but actually the point of this slide is just to reiterate the fact that the Stokes smoothing procedure, so this procedure where I optimally truncate the theta, optimally truncate the Q, and attempt to develop equations for the remainders, that typically is a universal procedure. And so you substitute this into the differential equation, you develop your L of Rn is equal to the right-hand side, or L of Sn is equal to the right-hand side, and you substitute in a multiple of the homogeneous solution, which you'll notice here, again, involves the big Q and the chi that you found before. There's this correspondence between the WKB form that you see here for the remainder and the late order ansatz that we used before. You optimally truncate and you localize near the Stokes line. So you write down, you do a change of coordinates so that when R is positive, and this theta is equal to 0, you're right on the Stokes line. And then you attempt to look at the differential equation for this prefactor A as you cross that Stokes line, as you rotate around the Stokes line from the negative theta to positive theta. And in doing so, you're going to predict that there has to be a jump of 2 pi I over epsilon to the gamma. And you can put this back into the full expression for the remainder and predict the resultant waves that form. The last comment I'll have on this slide is that you've predicted a complex exponential, an imaginary component for this Q epsilon, this exponentially small wave as you cross the Stokes line in the upper half plane. By reflection principle, because the solution is expected to be real on the axis, then you expect to also add the complex conjugate, and you could have equally done the analysis for the Stokes line in the lower half plane. Okay, let's say a few words about the Stokes lines, because it's a crucial quantity, right? So the Stokes line, as we said, is predicted by the location where chi, the imaginary part of chi that we found, is 0, and the real part of chi is positive. And we can just do it in mathematics. Yes, here we go. So we can just do it in mathematical. We put in our Q0 expression here. We can put in our chi expression and integrate it. And in this case, you can actually integrate it exactly in closed form. It's not always the case that you can do that. And then you can try to plot contours of this function. So here I'm plotting in red the imaginary part of chi equal to 0. So along this, there's a singularity at -1, which corresponds to the corner of the ship. And there's a Stokes line that emerges, or an equal phase line that emerges from that, these sets of lines. And then you need to verify in which region of the plane is the real part of chi positive, right? So if I go to these contours, this one's 0, this one's 0.81. This is the real part. The colors give you the real part. And so I notice the numbers are getting bigger. So that tells me that the Stokes line goes in the positive upper half plane and it loops around. This here on the right, this axis, this positive real axis, is your free surface. And therefore, there is a point across the free surface where you're expecting an exponential to switch on. And those are exponentially small waves that people have been looking for many years. Okay, so one can do numerical and asymptotic comparisons of this problem. You can try, the dots here give you the numerical solutions of the full nonlinear problem, and I can try to match that with my asymptotics for different angles of the stir. And that's a nice little fun exercise for you. I should point out by this graph, the gradient of this graph, the way I've plotted it, involving a logarithm of the amplitude at the top and then a 1/epsilon on the right here, you're expecting this gradient to be approximately straight in the limit that epsilon tends to 0 as you move towards the right there. And you can see that it is straight. So that is basically a confirmation of the chi component of your analysis, the e to the chi over epsilon, e to the minus chi over epsilon, right? And as I mentioned earlier, actually verifying some of these predictions is pretty difficult. It's actually quite hard to verify the Q function in front, or hard to also verify the epsilon to the gamma algebraic dependence on epsilon. And all bets are off for even trying to verify that prefactor that we said was very difficult to obtain. So there's a very interesting problem when you try to do exponential asymptotics for physical problems, which is that you predict certain quantities and computationally or experimentally, you may never be able to check whether your analysis is actually right or wrong if you're looking for independent verification. And that's kind of a difficult, that's why the problems are often very difficult. Okay, now the original Chapman and Vandenbroek 2006 study did it for flow over a step in a channel that you see here. And you can do those types of problems as well. This is a piecewise linear geometry flow over a step. And all it involves is an additional conformal mapping to change the relevant domain for the step to the upper or lower half complex plane. So most of these water wave problems, two-dimensional potential flow water wave problems over piecewise linear bodies, we can do pretty well, okay? I want to say two important comments about the figure here that you see. The first comment is that even though the Stokes line we predicted, we kind of did this analytic continuation process, and you have Stokes lines in the complex plane, you have switching across Stokes lines, right? There's a correspondence between the analytically continued plane and real space, which is not obvious, but is sensible. And so you can project the Stokes line into real space and predict that across this Stokes line, which is the same Stokes line that you derived, there are real waves that switch on, which makes sense, right? And one could perform, if you had the skill, one could perform a numerical experiment where you're resolving this to smaller and smaller values of epsilon. And the key is that if you were to resolve it to sufficiently small epsilon, you look at just the right location in the flow field, you will hopefully see the wave switching on. Moreover, if you had infinite computational power and you can look even further, you can even predict that the Stokes line has some finite width which scales with epsilon. That's the Stokes line smoothing procedure that Chapman demonstrated earlier. So you could try to do that experiment, but it's actually pretty hard. The second comment I'll make is the question of smooth bodies, right? So you present this theory to an engineer and they say, well, that's all fine and good. What can you tell me about actual smooth bodies? And this presents a very interesting problem that I think has kind of fundamental implications for some of these methodologies. So in terms of the question of how to approach smooth problems, there's kind of multiple answers I can give about that. The first answer is a bit of a flippant answer. So I look at this configuration, and this is for flow over a rigid step. Now I know that I can look at any interior streamline of the flow, so any of this light gray lines, and I can imagine that that streamline, because there's no flow that passes that streamline, I can imagine that streamline is itself the boundary of your domain, of your flow. And the solution that you've predicted has to be the same, it must be. And so therefore, this solution that you see here must be the free surface waves that corresponds to flow over a C infinity boundary, a smooth boundary that corresponds to one of these gray lines. It's a bit of a flippant answer, right? Because it doesn't tell you the actual inverse problem, which is what you're actually wondering about, which is if I were to draw you, if I were to give you a function, an arbitrary function, can you tell me that corresponds to the boundary? I draw you an arbitrary shape. Can you tell me what the free surface waves are? So it tells you the theory is not limited by the fact that your boundary has to be piecewise continuous. It'll work for smooth bodies, but it doesn't tell you much more than that. And I'll leave you with one final point about this, which is that analytic continuation is ill-posed, right? So here we took a solution along the free surface that corresponds, in this case, to a step, and we said, let's analytically continue this. Now, if you gave me one of the streamlines for the flow, I would tell you that the waves are predicted by a singularity that corresponds to a step that you didn't know existed, right? But I can also perturb that boundary by a very small amount. And because analytic continuation is ill-posed, you know that can introduce arbitrary singularities in the complex plane. So what does it mean when your exponential asymptotics is so highly contingent upon the distribution of singularities in the complex plane, and that's an ill-posed procedure to analytically continue in that manner? So that has some, I think, some important implications when you're trying to study flows through smooth bodies, and that's something that we're looking into at the moment. You can also make this problem a little bit more difficult. You can add surface tension into this problem. So now instead of Bernoulli's equation with just this first term involving the Froude number, I can add surface tension into the mix. And in doing so, basically I can introduce a whole range of additional effects, which now I have Stokes lines that may correspond primarily to gravity waves. I have Stokes lines that correspond to capillary waves. I can actually have interactions between the two. I can have intersecting Stokes lines. This is a complicated problem that we still don't fully understand, but it kind of shows you how this analysis can be upscaled and to develop some really interesting and intricate mathematics. Another note is I can do this without boundaries, right? So this here, I'm going to play this animation. This is what's known as the classic Stokes wave. So this is a wave that is traveling with constant shape towards the right, perhaps the most famous nonlinear water wave. Now we know that if you observe these kinds of waves in nature, that you have the picture towards the right, that near the crest of these waves, you can have little parasitic capillary ripples due to the influence of surface tension. And in '63 or thereabouts, Lonke-Higgins proposed that actually you can try to capture these parasitic capillary ripples using series expansions in the Bond number. So the kind of these classic initial attempts at trying to capture exponential asymptotics. So this is something that you can do. You can show that in fact there's a Stokes line that comes from a singularity above the crest of the wave that impacts the water, and that is the switching on of your little capillary ripples. And what's interesting about this problem, what makes it difficult, is that the Q naught and the theta naught that are involved at leading order must be determined completely numerically. So this relates a little bit in part. A few days ago, there was a lecture by Gerald Dunn where he talked about the need to develop schemes to find singularities in complex plane by Pade approximates and that sort of thing. So this is something of the same sort, where in order to do the analysis, the exponential asymptotics, you have to know something about the singularities, but you only have numerical solution along the axis. So you need to continue off the axis, find those numerical solutions, and go through with your scheme. Okay, so I've got a couple minutes left, or 2-3 minutes left. So in the last few minutes, I'm just going to touch upon one of the applications that John Chapman mentioned in his public lecture, in the public lecture last week. And the application, this is another classic problem. This is nothing new. This is a classic problem, another classic problem along the same lines as the Kruskal-Seeger crystal growth problem that kind of launched this area of exponential asymptotics and applications. So this is the 1958 experiment by Chapman and Taylor. You have a Healy-Shaw cell which corresponds to two very closely spaced pieces of plexiglass, and you put a viscous fluid on the interior and you pump air from the top. And what happens is that the interface, the air-fluid interface, goes unstable, and you have the development of these fingers that form. And Chapman and Taylor had the following thought. They said, well, let's assume that we can write down a toy model where each of the fingers is just simply propagating, and the adjacent streamlines, which you see here in red, you can think of it as a channel. So essentially, you think of a model where you have a single finger propagating in the channel. And the relevant non-dimensional parameter that comes up is this lambda parameter. This lambda parameter, which characterizes the relative size of the finger width here, marked in orange, with the spacing between the two red lines. And this is another problem. So earlier we talked about waterways. When you work with Healy-Shaw flows, flows in this configuration, that is also a potential flow problem. So you can also write down a boundary integral formulation, also involving a q and a theta. The speed of your interface, the angle of your interface is theta. And it involves this parameter of the finger width, this lambda, this kind of unknown parameter. And you can develop approximations in the limit that this capillary number tends to 0. So Chapman and Taylor wrote that the most interesting feature of the results exhibited is that in all cases, the value of lambda rapidly decreases as the capillary number increases till it reaches a value which is very close to a half. I think this is a typo, by the way, my typo. I think they meant the inverse capillary number, what they're referring to here. So the point here is that as epsilon tends to 0, right, what they find is that the finger width tends to a half the size of the channel. And they couldn't find a theoretical reason for this. And this is your beyond all orders effects. The basic idea to resolving this is that you have two equations now, your usual boundary equation for Q and for theta, and your Bernoulli equation. The independent variable here is y, where y goes from minus infinity to infinity to correspond to the interface. And you have certain symmetry conditions at the origin, and then a condition that theta flattens out at infinity. As Chapman and Taylor predicted, there is a leading order solution here, which is in fact this experimental picture. The dots are the experiments, and the solid curve is their asymptotic solution. So you see one order asymptotic solution looks fantastic. But the problem is that you have no restriction on lambda. Your asymptotic solution tells you that all possible finger widths are possible, even though you know that's not the case. In this formulation here, the lambda appears in the alpha. And so you can do the Stokes line analysis for this problem, and I leave that. You can look up, there are many, sorry, this is a well-studied problem from the 80s to the 90s. And the punchline is that there are two singularities, one in the upper half plane near where my mouse is, 1.5 here, one in the lower half plane, and those generate sets of Stokes lines. As I continue from the left to the right, I switch on a wave at the first intersection, and what switches on needs to be switched off in order to satisfy that boundary condition, and that is what produces the eigenvalue condition. So this is just a demonstration that the techniques that I demonstrated for you for water waves, you can equally apply those in a very similar spirit to the case of Chapman-Taylor viscous fingering, and they both use this kind of methodology that were introduced in lecture 1. That's it. Thank you very much.
Well, thank you very much for a very nice lecture, especially with the use of all kind of technology. That was pretty impressive. I don't see any questions in the Q&A, but if anyone has any comment, question, remark, let us know.
There is a raised hand, I think.
Sorry, I couldn't see it from here. Where is that? Ah, okay, sorry. I have a question. Yeah, please go ahead if you want to write it, or just unmute. Wait.
Can you hear me?
Oh yeah, sorry, I wasn't sure.
Sorry, yes, it's
Go ahead here.
Michael Berry. Well, thank you very much, Philippe. That was a really lovely account of all the various subtle effects you can get with these nonlinear waves. But when you showed these parasitic ripples, I noticed, and indeed I'm familiar with them, that the picture you showed, the photograph, shows them only on one side of each thing, whereas the simulation you showed shows them on both sides. Now, you can understand why they occur only on one side from linear theory. It's that the dispersion relation for little ripples on shallow water with surface tension and gravity there's a minimum of group velocity, so that the waves travel faster than the group, and you see them downstream of it rather than upstream as for longer waves. So why don't you see that in your simulations?
That's an excellent question, and I didn't mean to suggest that the problem has been resolved. In fact, the problem is open. So there's I think there's two answers to your question. The first is that in general, viscosity will tend to dampen the waves, and so you're not going to have an infinite train of parasitic ripples. The second is an open question, which is, let me take a steady state or a traveling wave approximation of the potential flow problem with gravity and capillary in there. Do there exist asymmetric solutions of that problem? Or do there exist, so there certainly exist symmetric solutions, which are the ones I showed you. The asymmetric solutions, I don't think, so this relates to current work. I think we've shown that asymmetric solutions will not exist in those problems, which suggests that perhaps the formulation is wrong. And what you need is a quasi-static formulation where the ripples are allowed to propagate on the solution of a steadily traveling gravity wave. But it's a very interesting question. And all I can say is that no one has given a very good answer to that problem. My feeling is that the steady formulation is incorrect, and you need a time-dependent formulation. You need to do your exponential asymptotics in a time-dependent formulation, allowing little ripples to propagate on the surface of the gravity.
Well, that's very interesting, because when you see, after the rain, water running down a sloping street, for example, then you can often see trains where there are quite a number of these maxima, each of which has ahead of it some ripples. And it seems to be a fairly static pattern moving downstream. Of course, as you say, viscosity suppresses there's only a finite number, but you do see them very clear. Okay, now will you allow me to make another more general comment? You see, there is a situation easily observed where you don't have any steps on the bottom, but still you can have a step on the top. And I'm referring to tidal bores. There's one near Bristol, which is world famous, and you can just literally see this pattern. And for many years, I've observed this, and I wanted to understand the shape. There's a very characteristic shape of undulations behind this moving front. And a couple of years ago, I did make a theory, and I wrote about it. And the interesting thing is that you can understand all the qualitative features with a linear theory. I mean, it turns out to be some linearization of KdV, but it's an unusual situation where the tide is coming in with one speed, and it meets the river flowing downstream with a different speed. Now, you can superpose ordinary linear waves given by the dispersion relation, but the superposition has to take into account the fact that at large distances behind and in front, you've got different depths. It brings a pole into the superposition. And then it turns out you need to use uniform asymptotics of the integral, and that's where the connection comes with this program. It turns out that after it's propagated for a long distance, which it does, I mean, many kilometers is a relevant parameter, which is several thousand when you see this bore. Whatever the initial shape, the emergent shape is the integral of an Airy function. Now, of course, the Airy function has in it all the oscillations on one side, but not on the other. So that's where the theme of this school comes in. And it turns out that this moving front is very closely analogous to horizons in relativity. you can have waves on one side, but not on the other. And it depends on whether the speed of the waves is greater or less than the speed of the water, and that is different downstream and upstream. So you can develop the theory linearly, quite accurately, and it doesn't involve all the subtleties that you've described, but it involves still the area function, which we know contains this sort of primordial Stokes structure. Just a comment.
Thank you. That means is very interesting. I should look into. I've known about some of that work, but one comment I'll mention is there is a connection between what you've said and some of the pictures I've presented.
Yes, indeed.
That when you study waves over a step, the traditional linearized theory assumes it's a single dispersion relation that relates the flow upstream and downstream.
Yes.
But when you try to do this kind of exponential asymptotics, it tells you that there is two different dispersion relations because the size of the step can be quite large. And so that's kind of, I'm curious whether there are links between what you've said about the undulating bores and these configurations.
Mm. Yes, well, exactly, because the dispersion relation involves the depth, and that varies. It's different on one side from the other. So that's all part of the story. And see, what frustrated me was that for years I've seen papers about tidal bores, and they're all nonlinear. And so you can do numerical calculations or whatever, but it's much simpler. You see it linear, and the slopes of these bores are very gentle. They're not sort of sharp fronts move. I mean, occasionally they are, mostly they're not. And they're just a few degrees, 10 or 12 degrees is the slope. So linear theory is reasonable, and it gives you a nice analytical formula from which you can get a large number of conclusions and predictions. That's it. Anyway, but thank you for your talk.
Thank you.
Thank you.
Yeah, sorry to interrupt. Maybe we should continue because we are running a bit over time. So there will be more time for discussion later on. So thank you very much again for the lecture.